All right. Well, let's try this out. So we're in chapter 24 talking about electromagnetic waves. And we've already seen some of these ideas, right? We saw last week that the idea of an electromagnetic wave is the electric field oscillations that are traveling forward in time. So the electric field showing is going up and down here. And then there's also oscillations in the magnetic field that are going in and out on this page, and again, propagating forward. And that comes from just having this AC source connected to two wires. That's one way we can generate an electromagnetic wave, that it creates a changing current going up and down, which generates electric field going up and down, and magnetic field going in a perpendicular direction. When both of those are perpendicular to the direction the wave is traveling, which is to the right there. We also saw that the speed of an electromagnetic wave, which foreshadowing is just light, in a vacuum can be given by c, is our constant for the speed of light. It's equal to 3.0 times 10 to the 8 meters per second. So this is a constant. It's actually one of the most constant things in all of physics. So it's a really great quantity to have. All right, so with this in mind of how these electromagnetic waves can travel, let's continue on. It turns out that they can be detected then by an antenna. So an antenna that could be like your car antenna, if your car still has an antenna that's visible. A lot of them are pretty hidden now. Or a TV antenna. They have wires that are made to line up with the electric field. And they then can take in the changing electric field, and it generates a current through this LC circuit. Now, you can adjust the dial on, say, your car's radio, right? You can tune it to different frequencies. And what you're tuning is you're adjusting the capacitor. And you're adjusting the resonant frequency of your particular circuit. Because when your resonant frequency matches the signal source, then you get resonance and you're able to then detect the audio or the video that's coming through. So this is the basics of how radios work, right? AM and FM, those numbers like 102.5, that's a number of hertz. I believe it's 102.5 megahertz or 91.5 megahertz. So that's the resonant frequency that you need to adjust to, and you could do the calculations to know what capacitance you would need to set to. But instead, we just have it already do the calculations for us. As we turn the knob, it tells us the frequency there. So that's how we can detect the electric field with an antenna wire. We also have ways to detect the magnetic field. So for the magnetic field, it's coming in sideways here. Instead of having a vertical stack of wires, we instead want a loop antenna, so that as the magnetic field pokes out one end of the loop with increasing or decreasing intensity, it generates a current through the loop. And then it goes the other way, generates a current the other way. And that will feed our LC circuit, where again, we can tune the capacitor to get the resonant frequency and detect the magnetic field of a radio wave. So both of these are in use. An example of this is on a ship's mast. You can see both vertical antennas as well as the loop antennas, because they want to collect all the signals possible. So pretty nifty. I didn't know that on the loop thing. I thought that was some sort of random enhancer for the wire antenna, but instead, no, it's actually able to detect the magnetic field of the electromagnetic wave instead. Another cool application of electromagnetic waves is cochlear implants, which are used with people who are very hard of hearing or hearing impaired. And the way it works is there's a microphone that's set usually into the ear mold, and so that detects the sound. The sound waves are sent to a speech processor, which transmits them into an electric form, into a radio wave that gets transmitted through the skull to the receiver that has an antenna that can detect those radio waves. And then the radio waves get connected by wire directly to the auditory nerve. So they bypass the hearing system, and this is a way that many people have been able to regain hearing or get hearing for the first time, which is pretty incredible. So, yay, electromagnetic waves. All right, so the next section is 24.2, the electromagnetic spectrum. And this graph or figure shows most of the big ideas. There's a lot packed into it. This shows the entire electromagnetic spectrum. So the top scale, the numbers here are frequency in hertz, versus the bottom numbers are wavelength in meters, right? Where we know that wavelength is how long each wave is going up and down, and frequency would be the number of waves per second. So those are inversely related to each other, and they follow the relationship that is true for all waves, right? The speed of any wave, v, is equal to the frequency of the wave times the wavelength of the wave. But for electromagnetic waves, the speed is already set by c, our speed of light, that 3.0 times 10 to the 8 meters per second. It's a good number to keep handy. It's going to pop up quite a bit. So what that means is, as our frequency gets bigger in number, because c is a constant, the wavelength has to get smaller. And sure enough, if we look at our frequency going to the right, the frequency is getting bigger and bigger, and wavelength on the bottom is getting smaller and smaller. And so then there are a bunch of words in here that fill in within these frequency ranges the different forms of electromagnetic radiation. The one we're most familiar with is the visible light, which is right in the middle here, right? Going from red to violet over a frequency of 4 times 10 to the 14 hertz for the red, all the way up to a higher frequency in violet, 7.9 times 10 to the 14 hertz. And then if you go beyond violet to higher frequencies, you get into ultraviolet, which is what is in the sun and causes skin cancer, right? That's why we want to wear sunscreen. You keep going to higher frequencies, you get into X-rays, which are what you take at the dentist's office or at the doctor's office if you break a bone. And beyond that are gamma rays, which are the most powerful, and hopefully you're not encountering too much. If we then go the opposite direction, below red is infrared. This is what's used in night vision goggles. Is also part of the solar spectrum. It's useful in heat. And then we can go down into the radio wave section, which is quite a large range. And you'll notice several different types of radio waves, right? We have AM, which is the lowest frequency, FM, which is a higher frequency by about 1,000 times more, and then microwaves, which is actually what is used to heat up your food. It's electromagnetic radiation, which sounds scary, but is basically light. So it's not all that scary. So this is a great chart to continue to reference to know how these different forms of electromagnetic radiation compare with each other. If they have higher frequency or lower frequency, smaller wavelength or higher wavelength. Okay, and this is a really neat side look from astronomy. This is views from different parts of the electromagnetic spectrum of the same object, right? So we have the visible down below. This is what we're most familiar with. But then we also have the view from looking at the X-ray radiation, the infrared radiation, and a radio wave there. And what we have here in all four views is this is known as the Crab Nebula. It's a remnant from a star that went through a supernova explosion about 1,000 years ago. So it's this trace, and astronomers can learn different things depending on which electromagnetic radiation they focus on. So there are some telescopes that are specifically designed for one of these forms of electromagnetic radiation, or there are some that have multiple forms, and you can filter it out depending on what you want to focus on with your particular look. All right, let's look at an example for the wavelength of visible light. So we want to find the range in wavelengths for visible light in the frequency range between 4.0 times 10 to the 14 hertz and 7.9 times 10 to the 14 hertz, right? Remember this was the red with the 4.0, and the 7.9 was our violet or purple. And this range in wavelengths we know is related to the frequency with our basic equation that's going to pop up again and again. This is a good one just to write down and imprint on your memory, that the speed of light is equal to the frequency times the wavelength, right? If we want to find the wavelength with this equation, we know the speed of light already, or the speed of electromagnetic radiation. We can divide both sides by the frequency and thus get the wavelength. So here's the equation set up with the wavelength is c divided by f. So we do it for the red first, and we notice that we get 7.5 times 10 to the negative 7 meters. But another unit that's often used with visible light, and as well as with light in general, is nanometers. This pops up quite a bit, so it's often useful to think of it. Instead of times 10 to the minus 7, we can make it 100 times bigger and make it times 10 to the minus 9, which is our nano prefix. And then for the violet, plugging in that frequency, we get 380 nanometers. So these are the basic ranges of the frequency of light, of visible light, right? It's going to go from a wavelength of just under 400 nanometers to just above 700 nanometers. So between 400 and 700 nanometers is where we are going to see visible light, which is pretty nifty. So those are good numbers to keep in mind. They're going to pop up a lot because we care a lot about visible light. All right, let's look at a conceptual example of the diffraction of AM and FM radio waves. So this one's a little bit challenging, I'll say that up front. Let's take a look. Diffraction is the ability of a wave to bend around an obstacle or the edges of an opening. Would you expect AM or FM radio waves to bend more readily around an obstacle such as a building? We notice we have our AM is here versus FM. And so the AM has a smaller frequency than the FM and a larger wavelength than the FM. Now, the reason I say this is difficult is because we haven't yet actually looked at diffraction. It's something that is sometimes covered very briefly in 2A. So let's take a look at the ideas of diffraction with sound. So this is not something you'll be directly tested on. It's just to get us another sense, an example of this, that we can look at diffraction that happens with sound, and it goes into speaker design. So within a speaker, the sound wave gets bent to different angles depending on the wavelength of the sound. So there's a larger angle, it bends out more with a larger wavelength. It's the important takeaway here. We know that because the speed of the wave, here the speed of sound instead of speed of light, is equal to the frequency times the wavelength, that if we have a larger wavelength, that's going to be a smaller frequency. So in terms of sound, this is again just a side. The higher frequencies, because they have a smaller wavelength, aren't able to bend to as large of an angle. And so they pass out in a pretty narrow cone that only someone who's faced right in front of the speaker can actually hear. Versus the lower frequencies, the longer wavelengths, bend to a larger angle. And so someone outside, as well as someone right in front, can hear those lower frequencies. Someone who's at a larger angle can't hear the high ones, they only hear the low frequencies. And so to help with this, speakers are actually designed for the higher frequencies. They make it a really small speaker, the tweeter, and that helps to bend it to a larger angle. And subwoofers are then going to be the larger, huge diameter because they're able to do that, and it helps the amplitude. But again, that's an aside. The main thing to take from this is that the wavelength is proportional to the angle of bending. So if we go back to this, we know diffraction is related to this bending around an obstacle, and that we get more bending with a larger wavelength. So pause for a moment and reflect on which answer you would say. Write down your answer. Go ahead and pause now. Okay, hopefully you paused. Now we can check the answer. I can't check that what you wrote, but I'm going to trust that you wrote something. So the answer is AM radio waves, right? AM radio waves have a larger wavelength, and so thus they bend more. And that's one reason why you don't need as many AM radio station towers, because they're able to travel much longer distances and bend around obstacles like mountains. Versus for FM, you need more frequent radio towers because they don't diffract quite as well. So there you have it. Thought that would be an interesting conceptual example that perhaps you could relate to. Don't worry too much about the diffraction itself. The more important thing here is understanding the difference in wavelength between the AM and the FM and how that can produce an effect. All right, we will wrap up there, but please ask questions in the discussion or send me an email, whatever works for you. I would love to hear from you. Bye for now.